Okay. Tell me.
Sir, I did not understand, like, actually, why. I did not understand the solution, how my answer is incorrect.
Mm-hmm. So
Just,
of course I don't know what you have done. I will just tell you what I have done. Okay.
yes, sir.
So the question is isothermal expansion, right? From the given state point. So let's. Okay. All right. So you draw the process on the PV first. This is essential to understand which phases are being visited, especially the two endpoints. Okay, so where those two endpoints lie, that is essential to completing the problem. So I believe point one is given 1.4 megapascal, 2.1. Okay, so 1.4 MPa and 305 Kelvin to 0.1 MPa and 305 Kelvin. Okay, so this is what is given to us. Now you can go to the data sheet. I will open at my end. If you want, you can open it separately at your end also. And check where does state point one lie. So ask for each individual state point separately. So ask for state point one and state point two. Look at the data sheet and tell me.
1.4, sir, 370. No, sorry. It is isothermal. So state point one.
Don't worry about isothermal right now. State point one, I have written both P and T. State point two, I have written both P and T.
Yes, sir.
So now you need to ask what is the phase of state point one.
Sir, it is liquid.
Okay, correct. Because at 305 Kelvin, the saturation pressure is 0.3 megapascal. Okay, so we are at above that pressure, so it will be liquid. All right, subcooled liquid, right? So let's
Yes.
and it's an isothermal process, so let's draw the isotherm also.
Okay, I understood my mistake. I have not taken latent heat of vaporization, I believe.
So this is
Latent
your
heat,
isotherm.
but I think I have missed.
So this is your state point one, and state point two at 305 Kelvin. Again, ask what is the saturation pressure? I just mentioned 0.3 megapascal, right?
Yes, sir.
So what is the phase in state point one?
Gas, vapor.
Right, superheated vapor.
Yes, sir.
Let's put that somewhere here. So now that means if I want to calculate the enthalpy change from state point one to state point two, I have multiple ways of doing that. Now, again, on the basis of given data, I have been given saturation data at 305 and 0.3 megapascal. Okay, it has been given that you can take liquid properties to be independent of pressure and use the values for subcooled liquid as that for saturated liquid at same temperature. Okay, so that is again on the basis of given information. So what I will do is I need to choose my path. I will start from subcooled liquid at 1.4 megapascal and 305 Kelvin. Now what is the next step? Take this
To take this to the vapor, sorry, yes, saturated liquid, yes.
at
At 0.3, yes, sir.
now convert this to saturated vapor at this condition only.
Okay, I missed this step. Okay.
And now convert this saturated vapor to the final condition, which is superheated
Superheated
vapor.
vapor.
Both pressure and temperature, sorry, just the pressure is different. Okay, so
Yes, sir.
that is my part. Now I'm going to label this as delta H liquid. I'm going to label this as delta H vaporization and label this as delta H vapor. All right. So for the liquid, you are having a change from 1.4 megapascal to 0.3 megapascal at 305 Kelvin. So use the relationships available for liquid, which if I take beta and VL to be constant, can be written like this. That is the only contribution because delta T term is zero. There is no change in temperature. Okay.
Yes, sir.
Delta H LV is anyways given. Now for the vapor, convert that into two contributions. Change for ideal gas between the same state points plus the residual at 0.1, which is the final state, minus the residual at 0.3. These two can be obtained from the Pitzer-Second video. And this is actually zero because delta T is zero. Okay. For delta S, this will not be zero because delta S depends on pressure changes also. So the formula will be slightly different. Okay.
So
And
can
then use the,
you,
yeah.
what? Okay, okay. I understand. Just give me 1 second. I need to recall this part. Okay, I got it.
All right. For delta S, you can repeat the same calculation, three contributions. The liquid part, again, use the same analysis. The answer will be slightly different, but procedure is not different. Again, I take beta and V to be constant. For delta S, vaporization part, enthalpy change of vaporization divided by the temperature of phase change. And for the liquid portion, for the vapor portion, again, two contributions, delta SIG, SR at the final condition. Again, I'm not mentioning the temperature, but SR will depend on both temperature and pressure. So temperature is because 305 everywhere, I'm not mentioning electricity. So delta SIG will not be zero. We have to use the formula minus R ln P2 by P1. Okay, where P2 is 0.1 megapascal, P1 is 0.3 megapascal. All right. So that is what it entailed. Delta H and delta S calculation.
Sir, why have you
Ideal
used residual properties in the calculation of the vapor phase for enthalpy?
because it is given, you have to use Pitzer second visual correlations. We are not modeling the vapor phase as an ideal gas.
Okay, okay, got it.
Okay, so we want to be more accurate. However, here what you will see is that the pressures are not too high. So therefore, the ideal gas contribution dominates.
Okay, that so you have ignored that,
I
I
have
think.
not ignored that, but even if you ignore that, you will not make an error in the answer.
Okay.
Okay. So that will be the ideal work. And from ideal work, if you want to go to actual work, this is a turbine operation, or this is a expansion operation. So in expansion operation, the formula would be multiply by eta because the work obtained would be less than the actual work.
Yes, sir.
So that was standard. You can use for the flow process the simplified energy balance. So from there you can get Q. Okay.
Also,
So,
sir,
so
in the
that
okay, got it.
All right. So first calculate ideal work, then actual work, then delta H you've already calculated, W you've already calculated, estimate Q, and then you can calculate entropy also. Okay. So all of this can be done. So, so even if you are maybe making mistakes somewhere here or somewhere there, other portions, if you have used these formulas, are being evaluated. Okay, so you're getting marks for other portions if, of course, these parts are correct. So even if there is some mistake in delta H or maybe some mistake in delta S, but other parts you've done correctly, then you will get marks for other parts. Okay, any other query on quiz problems?
Sir, in question 4,
Let me give time to just a moment. If
yes,
anyone else has before question 4 any question query, you can ask. Otherwise, I can move to question 4. So question 2, question 3, anyone else present here? If there is a query, please let me know.
Sir, question 2,
Yes.
second part, the CPV.
Okay. Yes. What is the query? How to
So the
calculate
query,
it?
yes, sir, yes.
General query. Yeah. Okay. Now, what do you think? How should you go about it?
Sir, I mean, I use the liquid data and then the enthalpy of vaporization.
Why you used? uh, So CP you can directly calculate from the enthalpy expression. So it's already given here, right? This is the formula you had to use. So HR as a function of T is available to me from Pizza second variable. Okay.
Okay, sir, got it, got it.
So if you look up the formula, let's say, I hope I'm writing it correctly. So I believe this is the formula for HR by R. Now all I have to do is take a temperature derivative of this. Because everything is in terms of TR. So you convert this to TR terms. So what will it entail? You divide by TC, multiply by TC. Okay, so the only benefit is everything on the right hand side is in terms of TR. Okay, even B is written in terms of TR. So from here now you can calculate the derivative. 1 by TC can be outside, P and R can be outside because you're calculating derivative at constant pressure. So you get dB by dTr, and on the second case you will get two terms. Minus dB by dTr, right? So this cancels out, and D also you can rewrite. So let me see if I have the final equation written somewhere. Yes, if I convert everything in terms of PR, TR, this last thing might have some error. I'm not sure. Okay, but that you can resolve yourself. Because again, the reason I'm using this form is because Pitzer second wheel correlations are giving you the value of BPC by RTC, which they represent by B tilde. Okay, so therefore I'm using this form. If you go to Pitzer second wheel correlations, the way those Pitzer second wheel correlations are written, this is the form where B hat represents BPC by RTC. Okay, so we just do that juggling so that I have this form. and now it's a simple thing. So if I need double derivative on B hat, it will be a double derivative on B naught. Omega is constant, double derivative on B1. So this is the formula you have to use to get to your answers. And the CPL and CPIG formulas were given, so you just had to substitute in there. All right. Question 3, any query? Question 4, now someone was asking. So what was the query on question 4?
Okay. So to calculate the new coefficient of performance, you
Mm-hmm.
have divided by you have divided uh, the standard coefficient of performance by like one minus this like 1 minus 35% in this case, like.
Mm-hmm.
But I want to understand, like I was confused that it needs to be 1 minus 0.35 or 1.7 divided by 0.35. I need to understand like why it was that. Like I first did. So
So don't do, I would say, rather than trying to guess, right? So just write what is given. So this is the definition of coefficient of performance. So for the total, entire work is coming from outside. So that is the total requirement of compressor. Okay.
Oh, I got it.
Now,
I got it. Like you have written that the turbo expander provides 35% of the work of the standard cycle. So the compressor does that 35% work less. So you have
yes,
done.
and QC note has not changed. Refrigeration load has not changed. So QC note stays QC note. And the work input to the cycle, you are correct, is decreased because the turbo expander is providing part of that work. Okay,
But
I will write plus sign. I will use plus sign because this quantity is negative. Okay,
got it. Sir, can
and
you
the
provide
magnitude of
some
this is
partial
given.
marks for this error?
I can't. It was a quite straightforward.
Yes, sir.
It's a 1 mark thing, and it's actually just one step calculation. So pretty much. So again, emphasis is on that. Don't try to guess. Just write first what is asked. So this is the part which is being asked. So why should I guess? I just write it as it is. Okay. So this is question, and the B and C both parts is one. Okay. So this cycle has been drawn already in the lecture class. From there, it's easy to see that both enthalpy and entropy would be higher. Okay. So is it clear? Part B and C,
Sir,
or you
why,
want?
like, how had you decided that it is higher? Like, I could not able to get the, uh,
It's in the lecture class. So if you go to the, let's look at this. I mean, you can plot the T on TS to get the entropy answer. I am plotting on pH to get the enthalpy answer. Okay. So it is given point 1 is same. So point 1 up to point 2, no change. 2 and 3, again, no change. Then you go up to, so this is, let's say, standard cycle. So for T, that is total. So this is the standard cycle. And now 1 is same, and I am putting turbo expander. Sorry, there is a small, there's an error here. Sorry. Okay, let's forego that top curve and put it yourself. Let's just do this. For the standard cycle, you have throttle. So this is where the four T lies. Enthalpy at 1 would be equal to enthalpy at 4T. Okay, now turbo expander work is being obtained. Okay, so there's a negative work. So what can you say about H1 minus H4TE? What is the sign of this? Positive or negative?
Work is negative.
W turbo expander, right?
Yeah.
Turbo expander would give you a negative work.
Yes, sir.
Okay. So H4TE must be greater than H1. That's it, lies somewhere here. The new cycle. Okay. So from 4T to 1, similar arguments you can present for entropy. Okay, you're going towards reversibility in the turbo expander part. Okay, so similar arguments, not same, but similar arguments you can use for the entropy part also. Okay, so you can see from here 4TE is greater than 4T. Correct answer is 4TE greater than 4T, which is enter 1. Okay, and for the entropy, use the reversibility argument. You are going towards reversibility. If it was a fully reversible process, entropy of state 1 would be equal to entropy of state 4. Throttle is more irreversible than turbo expander. So using that argument, you can say for sure that entropy of stream TE would be greater than entropy of stream 4. What else? This, I believe, is again kind of discussed in the class. Any queries on question 5, question 6? Adiabatic irreversible operation. Delta is total because it's irreversible. Must be positive. Delta S of surroundings is 0 because adiabatic. From here, I can conclude that delta S of the system in any adiabatic irreversible process does not matter turbine, compressor, or anything else in the world. I can give a general statement. Entropy change of the system in an adiabatic irreversible process would be always positive. In fact, this statement has been given in the lecture class also. Okay. Question 6 was discussed in the previous discussion session. So that's on the quiz. Anything specific from the problem sheet?
Sir, this is what I had to tell you. Sir, can we keep a doubt session, a larger doubt session of the problem sheets combined later, because we have a lot of evaluations this week. It is getting very difficult to um,
Later when?
um,
I mean, I can
let
do it
us.
next week. See, the problem is no one turns up. I from my side, I can schedule it.
No, sir.
Even
If we
today, I don't know how busy your schedules are, but in principle, at
actually what
1:05, I was ready to log out.
Yes, sir. Yes.
Oh,
What happened? Let me just clarify this, because today we had a offline class of MLL in the morning. Then we had a tute for fluid mechanics, which we have a upcoming quiz this week, and then we have to go to see our papers of the heat transfer course at 2 p.m. So we are not able to do it, because in the offline mode we have to go like very much, travel very much, And as now your lecture part has also been completed, I request you if you can keep a combined
I
tutorial
can.
session next week,
I
so all of us can attempt the tutorials before we come to the class, and then there can be a combined doubt session for the tudes, so that your time is also saved and we can also have a fruitful discussion.
sure I can do that. So tell me when. So I will want to do it before the last day of class, okay, just so that we are not in kind of contradiction of the semester schedule. So when is the last day of class?
I'll have to see that, sir.
Okay, let's. I mean, we can fix it now. So let me just try to
Sir,
open up the
I guess,
academic.
sir, I guess it's
Yes,
second.
second. So then it doesn't leave us much except for Monday, I believe. Let me just check. Monday is fine.
Sir, second.
Let me check. First, actually, second. Second might be before. Monday would be after the second semester. Two other than UG first year students. Okay. Last teaching day is actually this Friday. Right. Exams are starting from Tuesday. So in principle, yes, I can do it on Monday. Uh, but of course, or I can do it this Thursday. So what is preferable?
Sir, Monday is more preferable for me.
Entire entire class is going to say that. So let's. I mean, I
Yes,
can
sir. I
discuss
think
the.
I think the entire class would say Monday, because we have a quiz. Let me just give you our schedule. So I think you'll also agree with what I am saying. Um, so sir, we have a
See, I can agree. There will be a stray student who will then go and complain. I don't care, but there will be a stray student who will go and complain that sir kept the class on a day before major exam,
sir. I
where
don't.
all the problem sheets were discussed. Okay, so from my side, okay, I can do that. So what I will do? Okay, so
Sir,
let's.
why not on second Saturday evening or maybe in the afternoon?
No, Saturday I am busy. So what I will do is I will put the uh, model solutions, because again Saturday scheduling conflict will be there. I don't know what time, because it's a Friday timetable. We don't have a regular class on Friday. So I will put the model solution for this problem sheet also, which is the last problem sheet, PS8. Okay. PS7, this any query on PS7 right now? Otherwise, one problem I will discuss. If there is a specific query from the model solutions which have been uploaded, you can ask. Okay, so problem sheet 7, let's just take up one problem. P12 is easy. I will let you guys do it. It's quite straightforward. Let's discuss P13. You can read the problem statement. Take a couple of minutes, read the problem statement. So let me, what was the problem number again? P13. So broadly, this is the proposal that I have an aqueous solution contains PFBA in water. It will ultimately be equilibrated against oxygen, which is part of air. And I need to know how much oxygen is able to enter this aqueous solution. Okay, and then we can compare this number against the amount of oxygen that is able to get inside blood samples. Okay, all in vitro experiments. So we can, if the numbers are comparable, then we can say that this particular proposal of using a PFBA water aqueous solution can be used as artificial blood. Okay, where I might use it, maybe I'm trying to develop some artificial organs. Okay, and I want to check if those artificial organs can survive. So rather than using actual blood sample, maybe I will use PFBA plus water. Okay, as an artificial blood to just understand whether these organs which I have developed are able to survive or not. Okay, and then of course maybe later on you will go to in vivo experiments, everything. But at the first stage, if the simple combination can mimic dissolved oxygen concentration in blood, it saves me a lot of money and a lot of ethical issues also. Okay, so that is the broad idea. So first part is asking you on the basis of data given for oxygen equilibrated against pure PFBA, use this information to get the Henry's coefficient of oxygen in PFBA. So that is the first part which is given. So you write the Henry's law. Initially, the data is available for pure oxygen. So oxygen partial pressure is 1 atmosphere. So that is your left hand side. To get H1, I need to calculate X1, mole fraction of oxygen. It is given that 384 ml of O2 is dissolved. So use the ideal gas equation of state to calculate how many moles it is. So plug in the numbers. Okay, and this is present in 1 liter of PFBA. So now 1 liter of PFBA is equivalent to how many moles? Density is given. So this will correspond to 1883 grams. Convert this grams to moles. Calculate the molecular weight if it's not given. I believe the chemical formula is given. So from these two, you can get N of PFBA as 2.806. Use the moles of dissolved oxygen, use the moles of NFBA to calculate mole fraction of O2. And from there, you can calculate the Henry's coefficient of oxygen for PFBA. And this is the value I got. Okay, so that is part one. I have the value of Henry's coefficient for oxygen in PFBA. Not, okay, you can write it fully also if you want. Henry's coefficient of oxygen in water is also given. This data will already tell you whether PFBA will make any improvement. Larger the value of Henry's coefficient, lower is the solubility. So you can see that for water, this value is more than 100 times better. Okay, oxygen PFBA versus oxygen water, big difference. Okay, so I'm already seeing that adding some amount of PFBA in water can increase the amount of dissolved oxygen. Now the next part where we are asking how much. So for that we are going to make some approximations. So this is my system. Because not much is given to me, so I will say that dissolution of oxygen in the two components is independent. That means I can model the two parts separately. Okay, this is not fully correct, but because nothing else is given to me, how water is going to affect dissolution of oxygen in PFBA is not known to me. So therefore, we are taking this approximation. Okay. After that, the work is simple. So once I make this approximation, then all you have to do is calculate mole fraction of O2 in PFBA, mole fraction of O2 in water. You know the moles of water in the solution. So from there, you can get moles of oxygen in PFBA and moles of oxygen in water. So sum these up, you will get the answer. I will give you the final value. And again, we will discuss this part more, but I want you to try at least. But that will be the broad procedure. That since I know the Henry's coefficient individually, I can use those individual Henry coefficients to get the mole fractions individually in water and PFBA. From mole fractions, I can get the mole numbers, add up the mole numbers, and again, this might look very small, but that's all right. Gases have very low solubilities in liquids. Okay. And you can now convert it to volume also. In the problem, I am not asking further, but let's say you ask, did adding PFBA made any difference? So you can solve one more problem where you have air equilibrated against the water only, and again ask the same question. Moles of dissolved oxygen per liter of solvent. Okay. So ask the same question again. If the two numbers are not very different, you would claim adding PFBA was not helpful. If the two numbers are sufficiently different, you can say that adding PFBA was indeed helpful. Okay. So that's all then for today. Unless and until if someone has tried attempting any other problem from problem sheet 7, you can ask a question.
Sir, I haven't. So, whatever you decide regarding the timings of the tutorial session, please.
Let's try to decide here also. Four people are here, so all of you are okay with Monday, coming Monday, that is Thursday versus Monday. What is more preferable? All of you. You can, if there's a consensus here, then I can just decide that day. For me, it does not matter either day.
So the Tuesday exam is of this course, right? 1 to 1.
I don't know. Tuesday is this course. So then I would, I mean,
Yes,
personally, I would say Monday is pushing it too late. But again, I will go by, yes, let's say consensus of you four people. Thursday or Monday.
Sir, we
Okay,
have
let's do one
Viva
thing.
also on Thursday.
That is
Before
in the
that or
evening,
after?
yeah. No, it will be in the regular class. Okay, if I schedule
Okay.
it at another time, it will be another issue. So let's do this thing. we will have a session on Thursday. Okay. Uh, and if there are still some doubts remaining, I can do an extra session on Monday. That is coming Monday. All right.
Okay, sir.
That extra session on Monday would only happen if I a priori get confirmation of attendance. So I would ask on the class notebook. Even if there is one person who says, yes, sir, I am interested in the extra session on Monday, I will conduct that extra session. Okay. So we'll have the Thursday session. So please come prepared. Otherwise, I will only be discussing the new problem sheet, which is problem sheet 8. So problem sheet 8, I will discuss fully. From the previous problem sheets, I will take specific queries. All right. And then if there are still some doubts, I can conduct an additional session on Monday. All right.
Okay, sir.
And if you want on Saturday, I can, instead of Monday, I can conduct on Saturday also in the morning only. But so is 8 a.m. any other class on Saturday? It is Friday timetable.
So in morning we have quiz like on Saturday, I guess. Two.
Okay. So then Saturday we rule out, right? Then
10
Thursday.
to 11. It's 10 to 11. So like we could we could keep
I mean,
before that, before 10.
if you guys want, I can, instead of Monday, I can do it Saturday. Saturday 8:30 a.m.
But sir, I don't think everybody would be coming before class. They would be preferring after class because they will be preparing for quiz,
So
maybe
we keep
something like that.
Monday extra session. So let's keep Monday as the extra session. Okay. And this Thursday we'll have just the regular session where I will discuss problem sheet 8. Is that okay?
Okay, sir.
All right.
Sir, I
So
wanted to
problem. Yes.
ask for majors. It will be offline. It will be of 2 hours, and we can bring
Yes.
laptop for
No,
book
no, no, no. So
for.
if we are going to do it, uh, because we decided we'll do it pen paper. Okay, so not online. The exam we said we will do on pen paper basis, right? So it will be a subjective exam. So then the laptop will be provided by you. Sheets and your documentation will be provided by you.
So you are not audible.